to this lecture. This is lecture number 45. We are coming to the nearing the end of this course. Today in the last two classes we have seen primarily the photodetectors, photodiodes, pin photodiodes and APDs, which are widely used in optoelectronics and optical communication. In this class I would like to discuss some of the other detectors, miscellaneous detectors, other photodetectors refer to miscellaneous photodetectors, some of them very important, although not from the point of view of optical communication. So, the first of these, let me list some of the important photodetectors here. So, the photomultiplier tube PMT, the photomultiplier tube. We also have phototransistors, phototransistors. Then we will briefly discuss solar cells. We discuss solar cells because it is basically a photodetector which is operated in the photovoltaic mode of operation, as we will see. Then we will briefly touch upon quantum well QWIP, quantum well infrared photodetectors, and if time permits we will also discuss little bit about thermal detectors. These are basically a class of detectors, thermal detectors. So, let me start with PMT, because widely used photodetector, photomultiplier tube. The basic principle of operation, is first photoelectric effect. This is a photoemissive type of detector. It is a photoemissive type of detector. Photoemissive type. Photoelectric effect, which is followed by an avalanche multiplication process. Avalanche multiplication process. The photoelectric effect plus avalanche multiplication process here. So, let me illustrate the basic schematic of a PMT, and then we will discuss in detail. So, this is a photocathode. Photon is incident through a filter here, filter or a window. I will explain, it will become clear once I explain this. The photocathode here, this is a photocathode, The light to be detected is incident on the photocathode here, photocathode. The photocathode releases an electron, a photoelectron. As you can see, these are the diodes. These are, this is an anode, these are resistances, all equal resistances R. So, these are the diodes. This is a schematic representing the operation of a PMT. The incident photon releases a photoelectron provided the photocathode, the work function of the photocathode is smaller than the photon energy, or this is basic equation of the photoelectric effect is here. So, h nu is equal to E times phi m or W. So, this is the work function plus kinetic energy. So, kinetic energy of the electrons. If h nu is the energy of photons which are incident on the photocathode, if h nu is greater than the work function, then an electron with this much of kinetic energy is released. Now, as we see here, this is at a high negative potential, typically 1000 to 1000 to 2000 volt here, a power supply, and the subsequent diodes are at a lower potential or positive potential with respect to this, and therefore, they immediately get attracted towards the diodes here. The diode, the electron gains enough energy or a large kinetic energy because of the accelerating potential between them, that this leads to release of additional electrons. The electrons which are released here reach the next diode, move towards the next diode, because there is a potential difference between this, there is a resistance here, and therefore, they hit this diode with certain kinetic energy, and they lead to further avalanche multiplication. So, we started with one photon incident releasing one electron, which in turn releases further electrons, which leads to release of more and more electrons, and this kind of avalanche process takes place. Depending on the number of diodes, we have an avalanche which takes place. So, let me illustrate further that the avalanche is taking place. These are all electrons released, which are finally collected. As you can see, this is at a certain potential and this is connected to ground or the common line here, and therefore, this is again at the same potential, at a potential difference same as this one, and therefore, these are collected at the anode. So, the electrons from the last diode are collected at the anode. This leads to a photocurrent. So, this leads to a photocurrent and an voltage across. So, this is the load resistance R L, and this leads to an output voltage V O here. So, a single photon incident leads to creation of an avalanche of electrons. Typically in the entire thing, of course, the entire thing is housed in a tube. the entire thing is housed in a tube like this. Let me show you another diagram, but the basic principle is illustrated here, and typically a PMT, the tube contains 10 to 15 diodes. An accelerating potential difference of 100 to 200 volts between adjacent diodes. So, typically 100 to 200 volt accelerating potential. And typically 4 to 6 electrons, 4 to 6 secondary electrons. So, secondary electrons per electron, per primary electron, which releases 4 to 6 electron, which further multiplies 4 to 6 times, further multiplies 4 to 6 times. And therefore, the current gain due to one photon incident here, the current gain, if we let us say, so what will be the current gain? How do we calculate the current gain? So we have typically 4 to 6, let us call this as delta, equal to, and this is n equal to the number of diodes. Then the gain, the carrier gain will be equal to delta to the power n. So, if delta, for example, delta is equal to 5, if I assume. So, typically 4 to 6 electrons per primary electron is released, 5, and if it is 10 to 15 diodes. So, let me assume n equal to 10. So, this is 5 to the power of 10 is the gain, because one releases 5 and each 5 releases 5. So, it is 5 to the power of n number of diodes. So, this is nothing but 10 to the power of 10 divided by 2 to the power of 10. So, that is approximately 10 to the power of 7. 2 to the power of 10 is 32 into 32 is approximately. So, this is approximately 1000, 10 to the power of 3, and therefore, this is 10 power 7. So, the current gain G is approximately 10 to the power of 7, which means we have a large current gain. So, how does this number manifest in terms of the detection power? We can take an example and see the. So, let me erase this diagram here, and let me take an example. That was a schematic illustration. So, let me take an example. So, example. Let us say 1 picowatt, the incident power is 1 picowatt, P optical. Incident P optical is 1 picowatt. So, how to calculate what is the output across the load resistance? So, the typical responsivity of the photocathode material. So, let me before I continue with the example, let me talk about the photocathode materials. The photocathode must have work function W or E phi m, which should be less than h nu. So, if generally one uses cesium, so cesium, which has a work function of approximately 2 eV, that means up to 2 eV photons, 2 eV photons or above, photons with energy 2 eV or more than 2 eV are able to create electrons, lead to photoelectric effect. So, cesium, if it is about 2 eV, that means the wavelength corresponding to this is 1.24 divided by 2 eV micrometer. So, which means this is 0.62 micrometer. This means that light with wavelength 0.62 micrometer, that is 620 nanometer or less, 620 nanometer or less wavelength, 620 nanometer or less can be detected using this. So, indeed the responsivity, if we see the typical the quantum efficiency eta versus wavelength. So, we typically have 0.2, 0.4, 0.6, 0.8. So, lambda versus eta, the typical numbers are and the numbers here are about 0.1, 0.2, 0.2, 0.3 eta, the quantum efficiency of the detector. Quantum efficiency is of this order here. So, this is for cesium. If I take cesium, there are other materials. For example, one of the materials which is an alloy, a compound of sodium, potassium, cesium, antimonide. This has a work function E phi m. So, W is nearly equal to 1.42 eV, almost the same as band gap of gallium arsenide. So, but this is the work function. So, a photocathode material, this has about 1.42 eV. This means the lambda g is nearly equal to 1.24 divided by 1.42, that is nearly equal to 0.88 micrometer, 0.88 micrometer, which means it can go to about 0.8 or beyond, a little bit beyond 0.8. So, this is for this material and this is for cesium, and the curve which I have shown here is for this material, photocathode materials. But the important point to recognize is that the quantum efficiency is finite and usable quantum efficiencies are in the range of, in the visible range, primarily in the visible range. It is very difficult to find materials which have quantum efficiency, non-zero quantum efficiency beyond 1 micron. So, this is in fact one of the primary limitations of photomultiplier tubes is the range of detection wavelengths are limited to visible or near ultraviolet or very close to infrared. So, let me come back to this, because I wanted to show you what kind of numbers are in practice, what kind of numbers that we have for the quantum efficiency. And once we know the quantum efficiency, we can come back to this example now. So, I come back to the example. The example of what kind of voltage is generated at the output if 1 picowatt of optical power is incident. So, I go by the definition of quantum efficiency is equal to electron flux. So, I divided by E divided by incident photon flux, that is P optical divided by h nu, incident photon flux, and therefore, this is the photocurrent, primary photocurrent generated with this eta here. Therefore, we have I, the photocurrent, the primary photocurrent is equal to, we have eta into P op divided by h nu into E. So, that is equal to eta into P op divided by h into C by lambda into E, and we know this quantity here h C by E is 1.24 if lambda is in micrometer. So, this is equal to eta into P opt into lambda in micrometers now divided by 1.24. So, for an incident optical power, you can optical power P opt, you can find out what is the primary current generated by the photocathode, primary current generated by the photocathode. So, if I look at the previous curve, so these are typically 0.1 to 0.2. So, let me assume 0.2, eta is equal to 0.2. Incident optical power is 1 picowatt. So, 1 into 10 power minus 12, 1 picowatt, and the wavelength. So, let me assume the wavelength as 0.6 or 0.62. So, 0.62 divided by 1.24. So, this is the primary current, primary photocurrent generated. So, this is nothing but 2 and 2 goes here to 0.1, that means this is, so approximately 10 to the power of minus 13. So, I p is equal to 10 to the power of minus 13 ampere, the primary current photocurrent generated. However, the current which comes out at the output, so we have a gain of 10 to the power of 7. So, gain which is equal to I at the load resistance, I at the load resistance output current divided by I primary, this is equal to 10 to the power of 7. I assume 10 to the power of 7, the number which we have calculated here. So, 10 to the power of 7, and therefore, the current generated, therefore, this implies I load is equal to I p is 10 to the power of minus 13. So, this is simply 10 power minus 6 amperes. I load is equal to 10 power minus 6 amperes. So, recall that we have a tube, the PMT normally looks like this. There is a tube and a window at the top for photons to incident. So, this is incident photons, it is a tube, this is the PMT, schematic of a PMT now. So, incident, as soon as it is incident, there is the photocathode here. I am not showing the connections, electrical connections, but and then there is a diode here, a diode here, a diode. So, a set of diodes, and then the final anode. So, just recall that the incident photon generates an electron which then multiplies and gets attracted to this diode. From here it gets further multiplied to this diode, from there it is further multiplied to this diode. So, we have an avalanche of electrons which are coming, and finally, the last avalanche of electrons reach the anode, and this is the anode which is this is connected. So, normally there are terminals to connect the power supply and the cathode current. So, this is passing through the load resistance R L, and here we have the output. So, we have, or one can even measure the photocurrent which is coming out, or the voltage generated here. For example, if I take R L is equal to 1 mega. So, therefore, the voltage V out is equal to 10 power minus 6 into 10 power 6 is 1 volt. 1 volt is a very large output to measure. So, 1 picowatt can be easily detected by measuring the output voltage here. So, 1 picowatt incident here, by a considering typical numbers, we have calculated that 1 picowatt incident here generates a photocurrent, primary photocurrent of 0.1 picoampere, and then the current, because of the current gain, we have a current at the load of about 1 microampere, and across the load resistance we have about 1 volt. Indeed, one can easily detect power. I mentioned this, that output power of the order of 10 power minus 19 watts. We have already, this calculation was for 1 picowatt, 10 power minus 12 watt, and one can calculate, one can detect powers as low as 10 power minus 19 watts using a PMT. It is a very sensitive detector, but as I mentioned, the primary limitation of the photomultiplier tube is the material for photocathode, to find materials for the photocathode which can respond to infrared radiation. Work function of materials, sufficiently low work function of materials, it is difficult to find, and therefore, these are primarily used to detect very low levels of light intensity, very low level of light power in the visible region, the visible and spectroscopic in the visible region. So, let me quickly go to the next one, phototransistor. Phototransistor. Phototransistor basically is a transistor let me consider an NPN transistor here. Let us say silicon NPN transistor. The incident light is incident at this junction. The light incident at other junctions do not really contribute to the current, and therefore, the active junction is this one. So, this is an NPN transistor, this is the emitter, this is the base and collector. So, usually this end is forward biased, and in a phototransistor normally this is the load resistance. Normally, the base is not connected, because the incident photon flux does the same job as the base current. What the base current does to achieve transistor action, where we get a current gain because of the base current, is achieved by an incident photon flux. So, this can be understood more clearly if we look at the energy band diagram of this NPN junction. So, let me plot the energy band diagram here. So, this is a NPN junction. So, PN in reverse. So, we have this is the P region and the N region, and we also have here. So, this is the energy band diagram, E versus X. So, X is this dimension here. So, the Fermi function, this is the n side. So, Fermi level is here. So, before you applied any bias, the Fermi level is constant all around, and there is a steady state. The net carrier which is travelling in this direction is equal to the carrier flux travelling in the opposite direction. So, there is no net current, but when you bias here, so this is forward biasing this end. So, this moves up here, this end goes up or this end comes down. So, it is a relative bias. So, you have plenty of electrons here. So, plenty of electrons, there are holes here. So, holes, and again there are plenty of electrons, because this is n side. So, this is N, this is P and this is N. A photon flux which is incident on this junction here, that is, so let us look at this junction. So, this corresponds to the, this is the active area, that is the base emitter, base collector junction, PN junction. A photon which is incident here creates an electron hole pair. So, an electron makes an upward transition here. So, the incident photon, so let me show the photon incident h nu. So, in this region creates an electron hole pair. The electron which is here comes down the slope. So, the electron flows down the slope here of the potential slope. The hole which is generated here, the hole, the positive hole here, this moves up. So, we have all holes here. So, there are more holes coming here, there are more holes and an electron going here. More holes coming to the base region means this region becomes more positive or the potential energy is lowered. The potential energy is lowered, which means this barrier is lowered. When the barrier is lowered, so let me show the schematically, let me show the barrier lowering. So, the new diagram would, okay, or maybe, okay, let me show it here itself, the barrier getting lowered. So, this comes down here. Similarly, so the barrier is getting lowered. When the barrier is getting lowered, there is electrons which rush from here. Now, let me erase the earlier barrier. So, we can see now that the barrier has been lowered because of holes accumulating in the P region. The electron is flowing towards the N region, but the lowering of the barrier leads to an electron surge from the emitter side to the collector side. Normally, in an electronic transistor, this job is done by the base current. When you forward bias the emitter base junction, the barrier is lowered and consequently large current flows from N side to the, from the emitter to the collector, that is, carriers move over the barrier which has been lowered because of the base current. It is the same action which is taking place here, when because of the incident photon flux there are holes which are accumulating here and electrons moving here, and consequently this P region becomes more positive or the potential energy is lowered or the barrier is lowered, consequently large number of electrons move from this side to this side. So, the current in the external circuit here, so the current which is flowing, the current is depends on the incident photon flux, but the current is not just the primary current because of the two electrons which are generated or two holes which are moving. If two photons were incident generating a pair of hole and electron, then the primary current would be very low, but because of the lowering of the potential barrier, large electrons, large number of carriers move from the emitter to the collector, leading to a current gain. And this is the primary working principle of a phototransistor. So, in the last class we discussed about avalanche photodiode, and which has a current gain because of the avalanche process. Exactly like that, we see that the first two detectors which I have listed here, other detectors, the photomultiplier tube has a large gain again due to avalanche process. It is not a semiconductor PN junction diode, but it is a photomultiplier tube which works on the principle of photoelectric effect and avalanche process, and the phototransistor which works on the transistor action, which provides gain, also provides a overall gain to the photocurrent. Typical gains, current gains H F E is of the order of 200 to 500. The current gain is of the order of 200 to 500 in phototransistors. Phototransistors are used in certain simple applications where you have a sufficient amount of light incident, because one of the primary difficulties or demerits of phototransistor is that the junction area, the catchment area here, the catchment area is very small, because it is at the base collector junction, which is the active region. So, the area here is a small area photodetector. So, it is normally required to focus the incident light on to the junction, and secondly, it is a relatively slow device compared to pin diodes. Pin diodes are very fast, reverse biased pin diodes, because there is accumulation of charge in the base region. The accumulation of charge. So, these are the two merits, two demerits. One is small active area, small effective area, and 2 lower speed, low speed device, low speed because of accumulation of charges in the base region, because of accumulation of charges. In the base region. So, this is a device which is used for many simpler applications, primarily due to the photocurrent gain which is available with phototransistors. So, let me go to the next detector here, solar cell. Solar cell is not used as a detector normally, it is used for power generation, as all of us are aware, but its proximity to the photodetector operation that we have discussed, proximity of solar cell operation to the principle that we have already discussed in the operation of pin photodiodes, is what makes it very interesting. Solar cell. So, basically this is a PIN diode, or a PIN diode, and if we recall that the IV characteristics. So, this is the IV characteristics of the photodiode, then we have when there is a photon flux which is incident, then we have the scales on x and y axis are different. For example, here the numbers are say 0.5, 1 volt, 1.0, and here we are talking of 5 volt, -5, -10, and so on. Similarly, the current here is in microamperes. So, typically 50, 100 microamperes, and here the current is typically milliamperes, because this is the forward bias region and this is the reverse bias region. So, this is IS, the saturation current when there is no incident photon flux, phi is equal to 0, and this is for a photon incident photon flux phi 1, and because of that there is a finite photocurrent I p here. So, this is I p and this is I s, the saturation current I s, and another incident photon flux phi 2. We recall that there are two modes of operation of a photodetector, which we have already discussed, the photovoltaic mode and the photoconductive mode. So, the solar cells are operated in the photovoltaic mode without applying any bias, photovoltaic mode of operation. So, the incident photon flux here, incident on the photodiode, and there is a load resistance here to be chosen appropriately, and we have an output voltage V out. So, this is the photovoltaic mode, photo generated voltage. The photoconductive mode on the other hand had a reverse bias which we had applied. So, here, so this was V b, same photodiode, but now we have a bias voltage which is a reverse bias, and this is photoconductive. Mode of operation, photoconductive mode. So, if this is R L and if the diode current through this, the reverse current here I D. So, I D, if the reverse current, I am showing the reverse current I D, then we write V b plus the voltage across the diode V d plus I d into R L is equal to 0, or I d, the equation of the load line I d is equal to, we have I d is equal to V d minus V d by R L minus V b by R L. So, V d is this. So, the diode voltage, we plot V d versus I d here. So, this is I d and this is V d. So, this is the characteristic which simply says that this is nothing but, so minus 1 over R L into V d minus plus minus V b by R L. So, it is like, so this is I d, and this we have already discussed, is the equation of the load line y is equal to m x plus c, the constant. So, in this case, if I apply a reverse bias of 10 volt, then the load line would look like this. So, this is the load line. So, the slope of this slope is negative, is equal to minus 1 over R L, and this value here is nothing but this V b by R L, because when V d is equal to 0, I d is equal to V b by R L here, and this is V b. If V b turns out to be 0, if we, let us say we reduce V b to 5 volt, minus 5 volt, then this curve will shift here. The new load line will be this. If we turn off V b to 0, the load line will be here. And if we forward bias this, then the load line will be here. Please note that all of them are parallel. If we forward bias, then this will be the load line. The slope remains the same depending on, so this is reverse bias minus 10 volt V b, this is minus 5 volt, 0 volt, and this is forward bias, let us say 1 volt forward bias. So, in this case, in the first case, the Q point, so let me consider only one of them, for example. So, let me consider this, the case of phi 2, that is this curve only. There is an incident photon flux phi 2. So, I am just showing a dotted line to distinguish that. Incident photon flux phi 2 on this. So, the Q point, so the intersection of the load line with the characteristic I V characteristic is called the Q point, or point which is operation point, Q point is here. The Q point is here. If I have 5 volt, the Q point is here, and if I reduce it to 0, the Q point is here. Here is the Q point. So, Q point, and if I forward bias, the Q point is here. So, this is the Q point, the operation point. the point of operation if the incident photon flux is this. So, let me now draw only this one, only corresponding to this, and erase all the rest. So, here is the characteristic, and let me zoom this part of the fourth quadrant, because I am interested in solar cells, which means we are not applying any voltage, V b is 0. So, this will be the characteristic, and therefore, I am interested in the fourth quadrant here. So, this is the fourth quadrant, and let me draw that. It is a zoomed quadrant. So, here is the same ID and this is V d. So, the numbers just to, it is just zoomed. So, see that the numbers are small. So, this is 0.2, 0.4, 0.6, 0.8 volts here, and this is the current. So, we have, so let me write this as 20, 40, these are microamperes. So, this is microamperes, and here is the load line. There is a load which I had drawn, and this is the operating point. So, what does this mean? So, we are looking at this part, that is, we are looking at a photodetector, a photodiode here, and a load resistance across it here, and incident photon flux phi 2. So, the same curve I have expanded this part of the curve. So, we are in the fourth quadrant. So, this is the region of operation of a solar cell. There is no bias applied. Depending on the load resistance R L here, if an incident photon flux phi 2 is incident on the photodetector, then it will generate a current which corresponds to this and a voltage across the resistance here. So, this is the current and this is the voltage. So, let us say P m and I m, the photocurrent and the voltage. So, obviously, the slope is 1 by R L depending on the choice of R L. So, if I use a smaller R L, we will have a load line which is like this. So, this is for an R L. Now, this will be R L is equal to, let us say R L is equal to R 0 some number, then this will be R L less than R 0, and if I use a larger load line, that is if I use a larger resistance, then this will be the load line corresponding to R L greater than R 0. If I use a smaller resistance, please see that the current is here, the photocurrent generated is this much and the voltage across the load is this much here. If I use this as the R L, then the photocurrent generated is this much and the voltage generated is this much. So, the area under this rectangle, for example, let me show shade one of the rectangles. The area rectangle, that is the current I into the voltage, gives us the power generated. So, the power, electrical power generated. The electrical power generated because of the incident photon flux is given by the area of this, that is I into V. If I choose this as the R L, then the area would be this. So, let me do a reverse shading to show that the area is different here. So, the power generated will be this current multiplied by this. So, this will be, and if I use the other load resistance, I will have a area which is different. The point is, by an appropriate choice of RL, we can maximize the power generated, maximize the power generated, and this is an important consideration in the design of solar cells and circuits to collect the photovoltage that one applies that one gets. So, solar cell is basically a photodiode which is operated in the fourth quadrant and without any bias. So, an important issue is the load resistance, the choice of the load resistance from a circuit designer's point of view. The materials issues are there, materials issue are completely different. So, this is from a circuit designer's point of view to get maximum power out of this. So, the power generated. So, let me move over to the next detector. Very briefly, we are just discussing these various detectors. One can go for further details to various references, but these are very close to the discussion that which we already had. That is why I am just bringing them one by one. So, let me go to the in the remaining 10 minutes or so, let me go to the next detector, which is quantum well infrared photodetector. So, we come here, quantum well infrared photodetectors. These are photodetectors used in the IR, as the name indicates, used for infrared. They make use of inter-subband transitions in a quantum well device. If we recall, we have studied the quantum well structures earlier in detail. So, if we recall a quantum well, let us say for example, gallium arsenide and aluminum gallium arsenide, AlX gallium 1 minus X arsenide. Indeed, QWIP consisting of aluminum gallium arsenide and gallium arsenide quantum wells are widely used. So, if we have a large band gap, a small band gap material sandwiched between two large band gap material, we can obtain a quantum well depending on the dimensions of this layer here d. When d is smaller than or comparable to the de Broglie wavelength, then the energy levels are quantized and we have allowed energy levels here, which correspond to energy subbands. So, E1 and E2, and we also have similarly energy subbands or discrete levels in 2 dimension. This is X and this is E, and we have E1 dash and E2 dash, allowed energy levels for holes in the valence band E2 dash. And the interband, that is interband transitions take place from here to here, that is an energy level, lowest energy level, allowed energy level here. So, an electron from here can make a transition to the conduction band here to E1 and create a hole and an electron in the process. An electron which is sitting here, so this would require an energy difference which corresponds to this. So, this is the h nu should correspond to this. So, if we take gallium arsenide, as we know that this is about 1.42 Eg and therefore, this will be even larger than that. So, h nu is say 1.5 eV, approximately of the order of 1.5 eV. The energy difference here, this is of course not to scale, because the height of the barrier here, this is typically about 0.3 eV, 0.3 eV or 300 MeV, and therefore, the energy difference between the energy subbands here is quite small. So, this difference is could be 0.2 eV or 0.15 eV of the order of 0.15 eV, 150 MeV, which means the photons which can result in an electron going from E1 to E2 by absorption from one energy subband to the other subband correspond to a wavelength lambda, which is equal to 1.24 divided by 0.15 eV. So, this is in micrometers. So, that is something like, so this will be around 8 micrometer. So, 8 micrometer. So, we can see that we are in the infrared. So, when infrared radiation is incident on a quantum well structure like this, then the energy, there can be inter subband transitions within the conduction band, and photon can get absorbed by this inter subband transitions. So, the inter subband transitions, of course, unless we take away the electron from here, then only the process can continue, the process of detection can continue, and one of the ways to do this is by applying an electric field. So, application of an electric field, we have already discussed this in the context of electroabsorption modulators. So, application of E field, application of electric field. So, this leads to the energy band diagram tilting. Again not to scale. So, here is the first level and here is the second level. With the application of the electric field. So, the electron, so incident photon here, so H nu incident photon leads to an inter subband transition, an electron moves over to this level here. The electron which is here can either, because the potential barrier is now much smaller, the electron can spill over, that is thermionic emission mounting over the barrier, and then it will be swept to this end. The electron will be swept because there is an application of electric field. This side we have applied a positive and this side we have applied negative. So, the electron will be swept to the electrode on the where we have applied an electric field. It can also tunnel through the electron, because now the barrier thickness here is the very small. So, the electron could also tunnel through here and come out. But the important point is application of the electric field provides a means for thermionic emission or electron tunneling through the barrier and escape from the well, and therefore, there can be further photons which can be absorbed by the same process. So, the basic mechanism is this: an incident photon creates an inter subband transition, the electron which has moved to the excited level is ejected or moves over the barrier and is collected, which contributes to the photocurrent in the external circuit. So, the quantum well infrared photodetectors are based on this principle. Normally, one does not use a single quantum well, multiple quantum wells are used to enhance the effect. Always identical multiple quantum wells are used. We have already discussed this in the context of lasers, quantum well lasers and multiple quantum well lasers, that one uses multiple quantum wells to enhance the effect. several quantum wells. Similarly, on this side, so here are the levels. In each of the wells we have the same energy difference, provided they are identical. If the well width is the same everywhere, if they are identical, then the energy separation here between the two subband levels is the same everywhere, and therefore, the same photon can be photon of the same energy can be absorbed. So, the electron makes an upward transition and then a transition outward. So, there is a applied potential here, plus and minus. So, this is a multiple quantum well device. So, multiple MQW device which uses inter-subband transition to detect for IR radiation, for detection of IR. So, QWIP, we have discussed QWIP here, and you could go through details for other further details on these devices. And one sentence on, just we are running out of time. So, one sentence on thermal detectors. Thermal detectors are a class of detectors. The basic idea is simple, that there is an absorber, appropriate absorber. The incident radiation leads to a change in temperature delta T. This is the absorber. The incident radiation leads to a change in temperature delta T. So, delta T leads to a change in physical parameter, physical parameter of this material absorber here, physical parameter, and this change in physical parameter is detected. So, what is the change in physical parameter? What all parameters could be changing? For example, this physical parameter could be a change in dielectric constant, This could be a change in resistance, as in the case of, so this is in the case of bolometer. This is change in the dielectric. Pyroelectric detectors are based on this principle, pyroelectric detectors. This is bolometer. It could be a change in pressure, or any one of the physical parameters could change. For example, temperature, this could change in voltage, as in the case of a thermocouple. But the basic idea is this, that choose an approximate, it could be a mechanical change as well. For example, bimetallic absorbers could change, and correspondingly there could be a physical deformation depending on the change in delta T. So, this is sensed, the change in the physical parameter is sensed by different techniques, but the basic principle is just that incident photon flux leads to a change in temperature, which subsequently changes a physical parameter that is measured, and hence they are all of these fall under the class of thermal detectors. So, we stop here, it is time, and in the next class will be the last class of this course. So, we will we will just review and discuss photonic integrated circuits. Thank you.